Okay, here is the second part of the project, and this part concerns the computation of the counterbalancing force or torque and the reaction forces which act between the elements which are in contact with each other. So what is known in this case? First of all, the external forces are known. So in this case, the force P3 and the torque M3 are known loads acting on the mechanism. Also, when you have the link which has mass, like in this case M3 is the link with a mass, then you have also to consider the weight of this link as well as the inertia force, force due to inertia. What is this inertia force, or the moments of the forces of inertia? These are the let's say fictional forces which are introduced in the mechanism also to make use of the D'Alembert principle. I'll be talking about this in a moment, but first of all let's try to solve this mechanism using three different methods. So what you need, what you want to know is the force which you need to impose on the driving link to make the mechanism move with a given velocities accelerations which you assumed in the first part of the project. So first of all, if you have links with non-zero mass and non-zero moment of inertia, then you need to compute the weight, and the weight acts at the point S3. This point S3 is taken to be a center of the gravity of this object. Also, using the D'Alembert principle, when you need to apply a static analysis to the mechanism with a non-zero acceleration, you need to introduce these so-called inertia forces. So first of all, there is this inertia force acting on the link 3 at the point S3, and this is FB3 is equal to minus M3 times AS3. And of course, if there is also a non-zero moment of inertia and non-zero angular acceleration of a given link, then you need to compute the moments of the forces of inertia. It is given to as a equation, in this case minus J S3 times epsilon 3. I'll discuss this inertia force and the D'Alembert principle in general a little later. First of all, we have this graphical method. In the graphical method, to analyze the forces acting on the mechanism, he needs to decompose this into two parts. You have to detach the driving link from the rest of the mechanism, which is called in this case the structural group, and you analyze the equilibrium of the forces acting on the structural group as a whole, and then the same equilibrium acting on the driving link. Okay, so here first you start with the structural group. So you analyze the equilibrium of the forces acting on the static and on the two elements which are parts of the structural group. So as you can see, you need to introduce all of the external forces acting on this structural group. So this is the force P3, there is a moment M3, there is also a weight of the link number 3, and the moment of inertia, no, not the moment of inertia, but the force of inertia acting at the point S3, and the torque due to the forces of inertia mb free. When you draw the free body diagram for the structural group, you need to replace the constraints with reaction forces. So there are two points at which the structural group was connected with the rest of the mechanism. The first is the point C. Here there is a rotational joint at this point, therefore you don't know the direction of the reaction force, because the reaction force depends on the point at which the two rotating surfaces connect to each other, and this point depends on the overall forces acting on the mechanism. So you have to assume that you don't know the direction of this force. But you need to use two components of this reaction force which are perpendicular to each other. And in this graphical method there is a convention that the first of these forces must be parallel to the BC, and the line of action of this force must pass through the point B. So the second is perpendicular to this one, so you have two reaction forces, R0 free normal and R0 free tangential. When you look at the point B, here there is also a rotational joint, but I assumed that the direction of this force is perpendicular to the BC. And why? When you look at the slider and the rod free, you see that these two elements are connected by a translational prismatic joint, and we assumed in this analysis that all of the joints between the elements are frictionless. Therefore, when you have two sliding surfaces, the only reaction force is normal to the let's say surface of the contact between these two surfaces. So you know that this rod number 3 must act at the slider on the slider by a force R32, and this force must be perpendicular to the rod BC. When you look at the slider as a element which is let's say in the static equilibrium on its own, you see that there are no weights, there are no inertia forces, there are no friction force, so there is only one force acting on this slider coming from the rod, and the only force which has to equilibrate this force comes from the rod 1. So there are two forces acting on the rod on the slider 2. One is R32, which comes from the contact of the rod with the slider, and the second one is R12, which comes from the contact between the rod 1 and the slider at this rotational joint. But because first of these forces, this force due to the rod 3 acting on the slider, must be perpendicular to BC, so to equilibrate these forces, R12 must be also must have the same direction but the opposite sense than this force. So this analysis tells you that R12 must be also perpendicular to BC. I can also look at the next slide when in the analytic method it is drawn more clearly. So maybe here you can see this is the slider. There are two forces acting on this slider because of the fact that the connection between the rod and the slider is frictionless. There R23 and R32 must be perpendicular to BC, therefore R12 must also be perpendicular to BC. So we have three unknown reaction forces. We can write the vector sum of these forces. Due to the D'Alembert principle, we can solve it using the static equilibrium equation. So the sum of all of the forces is equal to 0. You know, but when you look at these forces, you know the directions of all of them, but you don't know the values of three of them. So you cannot solve this vector equation. You have to find one of the unknown forces. So let's look at this structural group drawing and look at these three forces. So you need to compute the moments of one of these elements. Maybe okay. So you need to compute the moments of all of the forces acting on one of these elements with respect to the point which is common for these 2 points, for these 2 elements. So you take the link number 3, you have to compute the torque of all of the forces acting on the link number 3 with respect to point B, which is common for both the link number 2 and link number 3. Also, in this case, I think this is the only thing we need to do, because as you can see at this equation of the torques of the forces, you see that MB3 is equal to P3 times DC minus and the other forces and the other torques due to other forces. So you need to include first of all G3, FB3, P3 and R0 3T. So these are the forces which produce a torque with respect to B. When you look at this R0 3N, the torque of this force is equal to 0 because the line of action passes from point B, and also for this reason the torque of R12 with respect to point B is equal to 0. So when you look at this equation, of course there are also some torques M3 and MB3 which are given and also act on the element 3. So when you look at this equation, some of the torques of these forces are equal to 0. Then you can compute the R0 3T, because this is the one equation with one unknown, and this unknown can be easily computed using this equilibrium of the torques. Okay, and I have to one thing needs to be clear. First of all, you analyze the sum of the torques of the forces but acting only at the element 3, and this sum is equal to 0. If in the other project you also have the case when there is more complex element number 2 and maybe there are even more unknown reaction forces, to compute one of these reaction forces you need also to compute the equilibrium of torques of these forces acting only on the body number 2 with respect this common point between link 2 and link 3. Okay, so after this computation we have only 2 unknown reaction forces. We know the directions of these forces, so you can graphically solve this vector equation, and here there is a solution for this vector equation for our structural group. After that we have to go to the second element which needs to be analyzed. So we need to analyze the static equilibrium of the driving link, and as you can see there is one known force acting on this driving link, R21, which is known from the previous analysis. and there are three unknown reactions. R01 is the unknown reaction, Fr is this driving force which is needed to be computed, and M01 is also needed because this is a case like in the cantilever beam, so here also there is some non-zero reaction torque acting on this slider, because the slider, due to the reaction force R21, tends to rotate, and this tends to generate the reaction torque also. And because these are only three forces, we can solve this using our sum of the three forces method to compute R01 and Fr. These two forces are found by the graphical method, and the unknown M01, this reaction torque, is computed by analyzing the sum of the torques with respect to the point A. One thing I need to also remind you is that you need to also, in the computation of all of the torques of forces with respect to the given point, you need to consider only this perpendicular distance between the force and the point of computation of torque. And therefore, there are these H1, H2, and on the second slide, H3 directions, which you can measure using your drawing, or you can compute knowing the angles between the forces and this, let's say, element BC. Okay, so this is the method, the graphical method. And the kinetostatic can also be solved using the analytic method you learned during your static course, because you remember that when you have a let's say structure at the static equilibrium, then to analyze the reaction between all of the elements of the structure, you have to assume that all of the forces, the external forces as well as the reaction forces, summed over should give you 0. And you know from the statics the so-called free body diagram method. When you have a complex structure, you let's say disassemble the structure into its elements, and for each of the elements you have the static equilibrium equations. So sum of the forces along the x, y, z axis are equal to 0, and also the sum of the torques are equal to 0. But in case of our mechanism, these mechanisms are not the static equilibrium. They are mechanisms, not the structures. So this static equilibrium equation does not apply to them. What applies to them is the Newton equation of motion. You know that the sum of the forces is equal to m times a. This is the Newton's second law of motion. And similarly for the torques, you have the Newton equation that the sum of the torques is equal to I times the epsilon. So these are not sum of forces and equal is equal to 0. So therefore this method could not be applied to the mechanism. But there is one principle which was introduced to the mechanics by Jean-Laurent d'Alembert, the French mathematician and the physicist, the so-called d'Alembert principle. D'Alembert realized that if you have this F equal ma equation, let's say that we are talking about the material points, not bodies. So if you have this F times ma equation, then you can just move the ma to the same side of the equation as the other forces, and you have exactly the static equilibrium equation. You have the sum of the forces, meaning the force due to the some of the forces due to external loads, plus some of the forces due to the reaction between elements, plus something which is called minus m times a is equal to 0, and he called this minus m times a the so-called inertia force. This inertia force is not the real force, it's just, let's say, a mathematical convenience to change the dynamic, let's say, problem into the static one. So if you introduce this reaction inertia forces as equal to minus m times a, as well as the torques due to reaction forces equal minus I times epsilon, then you can treat this as extra forces acting on the mechanism, and you can just analyze the static equilibrium of all of the forces. You may recall from your electrostatics or electricity course that there is something very similar in the case of the Kirchhoff's laws. So you know that you have the so-called closed electric circuit, then the sum of the voltages across this circuit is equal to 0. But this is also true only if there is no inductivity, there is no induction phenomena in the circuit. In case of the induction, the sum of the voltages is not equal to 0, it is equal to the L times di by dt, so this let's say induction effect. But we can also move this L di dt to the left hand side of this Kirchhoff's equation, and we can treat this as a voltage on the inductor, and you can also analyze that the sum of the voltages is equal to 0, which is not true, but this is also a mathematical convenience for the analysis of the electrical circuits. And the same case is done in the case of the D'Alembert principle. Okay, so when we know that we can use your knowledge from the statics to solve this problem, when you introduce the inertia forces and the moments of the inertia forces to have this dynamic effect, then you can proceed and use the free body diagram method to solve the problem. So you take this mechanism, you disassemble it into 3 different parts, you introduce the reaction forces in place of the constraints, and having all of the constraints replaced by the reaction forces, having all of the external forces, and also the the inertia forces acting on the mechanism, you can solve this by composing a system of equations of the static equilibrium. Of course, don't remember about the Fr. Fr is this force which drives the entire mechanism, and this is also unknown to us. So in general, we have the planar mechanism, we have 3 elements, so for each of the elements we have 3 equations of the static equilibrium in this new D'Alembert sense. So in general we have 9 equations and 9 unknowns, and you know that using the third law of motion of Newton, you can reduce the number of unknowns to 9 in our case. When we look at our particular example, we see that in our particular example there is a less number of unknowns and less number of equations due to this particular connection between the slider, which is massless, and the slide and the rod number 3. So we have of course one thing more. Remember that in order to analyze this static equilibrium using analytical method, you need to have the same frame of reference for each of these elements. So you have some global frame of reference, and in this global frame of reference all of the forces must be analyzed. Therefore, taking one frame of reference, I've just taken some of them, and knowing the geometry, knowing the angles, I can write, in case of our mechanism, 7 equations, and there are 7 unknowns, so this mechanism can be solved using the methods for solving the linear system of equations. Okay, so let's talk about this last point of this kinetostatic analysis. This is the so-called method of instantaneous power. This is the method which was computed also by D'Alembert and also by the Lagrange, and I think that let's say this is based on the principle of the virtual work, and I think this was introduced and derived during the lectures, so I just tell you about the practical application of this method. So this method lets you to eliminate the internal forces, reaction forces acting between the links of the mechanism. Because using this so-called method of virtual work, you will see that the sum of the reaction forces, the sum of the work of the reaction force is equal to 0 in case of the no friction between parts of the mechanism. You know, these forces are equal and opposite, so when the displacement when there is some displacement and there are two forces acting at this displacement, but one is, let's say, upwards and the second is opposite downwards, these works have of these two forces on the same displacement have equal and opposite values, so the sum of the works is equal to 0. So when you analyze the work of all of the forces acting on the mechanism, the work of the internal forces gives you the 0 value, so they have to be let's say removed from our equation. And the instantaneous power method says that in case of the dynamic equilibrium, the sum of instantaneous power of all forces, meaning external, weight and inertia forces, is equal to 0 at each moment of time. So when you look at our equation, we have to compute the sum of the powers of all of the forces, and you know the power of the force is the scalar product between the p force and the velocity, or is the scalar product of a torque times the angular velocity. So if you sum up all of the forces, of all of the powers of the forces, they should give you 0. So you assume that the only non-zero powers comes from the external forces, in our case P3, M3, and also this Fr, the driving force, plus the powers of the weight, gravity forces, G3, times the power plus the power of the inertia force, here given FB3. This sum must give you 0. And if you look at this vector, not vector, I'm sorry, the scalar equation, you know that you know all of the velocities which are inside in this equation because they have been computed in the previous step. You know also weights, external forces, all of this inertia stuff and so on. The only unknown is Fr, this counterbalancing force. So you have one equation with one unknown. You can solve this very easily to find only the value of the counterbalancing force and torque. Because the no reaction forces are found in this procedure is usually done in order to find the drive, the power, let's say the force, torque, and the power of the drive, which is necessary to apply to have the mechanism moving as you wish. And of course, as you can see, there are cosines, but you also know the angles between all of these forces and the velocities. So this is the last step in the case of the static kinetostatic analysis, and this ends the procedure which is necessary to find the drive for your mechanism, as well as find all of the reaction forces which maybe are useful for a let's say finding the strength uh, of each of these elements and necessary cross sections, for example. I think that's all for